The stream function is defined for incompressible flows in 2 dimensions as well as in 3 dimensions with axisymmetry. The flow velocity components can then be expressed as the derivatives of the scalar stream function. The stream function can be used to plot streamlines, which represent the trajectories of particles in a steady flow. The 2-dimensional Lagrange stream function was introduced by Joseph Louis Lagrange in 1781. The Stokes stream function is for axisymmetrical 3-dimensional flow, and is named after George Gabriel Stokes. Considering the particular case of fluid dynamics, the difference between the stream function values at any 2 points gives the volumetric flow rate through a line connecting the 2 points. Since streamlines are tangent to the velocity vector of the flow, the value of the stream function must be constant along a streamline. The usefulness of the stream function lies in the fact that the velocity components in the x and y directions at a given point are given by the partial derivatives of the stream function at that point. A stream function may be defined for any flow of dimensions greater than or equal to 2, however the 2-dimensional case is generally the easiest to visualize and derive. For 2-dimensional potential flow, streamlines are perpendicular to equipotential lines. Taken together with the velocity potential, the stream function may be used to derive a complex potential. In other words, the stream function accounts for the solenoidal part of a 2-dimensional Helmholtz decomposition, while the velocity potential accounts for the rotational part. 2-dimensional stream function definitions. Lamb and Batchelor define the stream function in the point with 2-dimensional coordinates and as a function of time for an incompressible flow by. So the stream function is the volume flux through the curve, that is, the integral of the dot product of the flow velocity vector and the normal to the curve element. The point is a reference point defining where the stream function is 0. A shift of results in adding a constant to the stream function. An infinitesimal shift of the position results in a stream function shift, which is an exact differential provided. This is the condition of zero divergence resulting from flow incompressibility. Since the velocity components have to be a and a in relation to the stream function, definition by use of a vector potential, the sign of the stream function depends on the definition used. One way is to define the stream function for a 2-dimensional flow such that the flow velocity can be expressed through the vector potential. Where if the velocity vector in Cartesian coordinate system this is equivalent to where and are the velocities in the and coordinate directions, respectively. Alternative definition. Another definition is, where is a unit vector in the direction and the subscripts indicate partial derivatives. Note that this definition has the opposite sign to that given above, so we have in Cartesian coordinates. All formulations of the stream function constrain the velocity to satisfy the 2-dimensional continuity equation exactly. The last 2 definitions of stream function are related through the vector calculus identity. Note that in this 2-dimensional flow derivation of the 2-dimensional stream function, consider 2 points A and B in 2-dimensional plane flow. If the distance between these 2 points is very small, in, and a stream of flow passes between these points with an average velocity, q perpendicular to the line AB, the volume flow rate per unit thickness, II is given by as INA0, rearranging this expression, we get. Now consider 2-dimensional plane flow with reference to a coordinate system. Suppose an observer looks along an arbitrary axis in the direction of increase and sees flow crossing the axis from left to right. A sign convention is adopted such that the velocity of the flow is positive. Flow in Cartesian coordinates, by observing the flow into an elemental square in an xy Cartesian coordinate system, we have where u is the velocity parallel to and in the direction of the x-axis, and v is the velocity parallel to and in the direction of the y-axis. Thus, as INA0 and by rearranging, we have flow in polar coordinates, by observing the flow into an elemental square in an Ra-I polar coordinate system, we have where Vr is the radial velocity component, and y is the tangential velocity component. Thus, as IRA0 and IIA0, by rearranging we have Continuity, the derivation, consider two-dimensional plane flow within a Cartesian coordinate system. Continuity states that if we consider incompressible flow into an elemental square, the flow into that small element must equal the flow out of that element. The total flow into the element is given by. The total flow out of the element is given by. Thus we have. And simplifying to. Substituting the expressions of the stream function into this equation, we have. Vorticity, the stream function can be found from vorticity using the following Poisson's equation. Or, where the vorticity vector defined as the curl of the flow velocity vector for this two-dimensional flow has that is only the component can be non-zero. Proof that a constant value for the stream function corresponds to a streamline. Consider two-dimensional plane flow within a Cartesian coordinate system. Consider two infinitesimally close points and. From calculus we have that. Say takes the same value, say, at the 2 points and, then is tangent to the curve at and. Implying that the vector is normal to the curve. If we can show that everywhere, using the formula for in terms of, then we will have proved the result. This easily follows. References, in line. Other.